Voltage and current are related by impedance in electrical circuits. But what is the equivalent concept for electromagnetic waves traveling through space? Surprisingly, electromagnetic waves also have an impedance. Understanding wave impedance is essential for analyzing wave propagation, reflections, antennas, and RF system design. In previous lessons, we learned that electromagnetic waves consist of electric fields and magnetic fields propagating together through space. We also saw that these fields carry energy and information from a transmitter to a receiver. However, an important question remains. If both electric and magnetic fields exist within the wave, how are they related? Does a stronger electric field always imply a stronger magnetic field? Is there a fixed relationship between them? Answering these questions is crucial because the balance between electric and magnetic fields determines how electromagnetic waves interact with materials, antennas, and transmission structures. This relationship is described by a quantity known as wave impedance. Wave impedance is the ratio of the electric field strength to the magnetic field strength in an electromagnetic wave. Instead of relating voltage and current as in circuit theory, wave impedance relates electric and magnetic fields. It describes how much electric field exists for a given amount of magnetic field during wave propagation. In free space, this ratio has a constant value of approximately 377 ohms. This value is known as the intrinsic impedance of free space. Different materials have different wave impedances because their permittivity and permeability affect the balance between electric and magnetic fields. Intuitively, wave impedance can be viewed as the field balance of an electromagnetic wave. Just as electrical impedance describes the relationship between voltage and current, wave impedance describes the relationship between electric and magnetic field strengths. Physically, imagine two electromagnetic waves carrying the same amount of energy. One wave may have a relatively strong electric field and weaker magnetic field, while another may have a different balance. The wave impedance determines this relationship between the fields. Mathematically, wave impedance depends on the medium's permeability and permittivity. Since these material properties vary from one medium to another, wave impedance also changes. This variation plays a major role whenever electromagnetic waves encounter boundaries between different materials. Wave impedance is extremely important in RF engineering because it directly influences wave reflection and transmission. Whenever an electromagnetic wave encounters a material with a different wave impedance, part of the energy may be reflected. This concept explains why impedance matching is so important in antennas and transmission lines. Engineers try to minimize reflections by ensuring that electromagnetic energy transitions smoothly between components with compatible impedances. At the system level, wave impedance affects antenna radiation, microwave circuits, waveguides, radar systems, wireless propagation, and electromagnetic compatibility. Many RF design techniques ultimately aim to control impedance relationships and maximize power transfer. Wave impedance provides a bridge between electromagnetic fields and practical RF engineering. It transforms abstract field concepts into quantities that engineers can use to predict reflections, power transfer, and propagation behavior. A common misconception is that impedance only exists in circuits and transmission lines. In reality, electromagnetic waves themselves possess impedance, even when traveling through free space far from any conductor. Understanding wave impedance prepares us for an even more important question. How much energy is actually carried by an electromagnetic wave? In the next lesson, we will explore power in EM waves and discover how electromagnetic fields transport energy through space. In this lesson, we learned that wave impedance describes the relationship between the electric field and magnetic field within an electromagnetic wave. We also saw how wave impedance influences reflections, propagation, impedance matching, and RF system performance. In the next lesson, we will explore power in EM waves and discover how electromagnetic waves carry energy from a transmitter to a receiver. If you found this useful, like the video, subscribe, and follow for the next lesson.